Okay, so the last topic I want to cover in the conservation of energy is pump and turbine sizing. And I'm going to go specifically over pump sizing, and turbines really work kind of the same way, it's just in the reverse order. So when you want to size a pump, you typically have some sort of engineering problem like we have set up here, where for this example we have a large reservoir, we have some pump that's piped with some piping system that's pumping water to a large tank, say, that's elevated, so say a water tower for a city water supply. Okay, and so the way you would size a pump is a lot like the problems we've already been doing. We start with the conservation of energy equation. So we do that. We say Q dot over M dot G plus U1 over G plus P1 over gamma plus alpha 1 V1 bar squared over 2G plus Z1 plus H sub P is equal to P2 over gamma plus alpha 2 V2 bar squared over 2G plus Z2 plus H sub L plus H sub T plus U2 over G. And then we're going to go through the same thing we've done in previous examples, where we're going to get rid of some terms. And when you're doing pump sizing, you can't always get rid of some of these things, because pumps and turbines, they'll add and take out energy to the system, so the water might be warmer due to some heat losses in the pump because the motor is going to get warm. So you can't always ignore the heat transfer, but for this class we're doing fluid mechanics and we're going to focus on the mechanical losses, and so we can assume no heat transfer. We can also assume the internal energy is not going to change. And again, if you move on to thermodynamics or heat transfer classes, that's going to change, and you're going to have to start dealing with some of these more often. And you saw in one of the earlier examples for this class where I went through that process of dealing with the heat transfer and the enthalpy of the system. Okay, so for this particular case, our points 1 and point 2 are going to be these free surfaces, right? So we're going to have a free surface here and here, so that'll allow us to get rid of the pressure. And I'd like to point out, if you're doing pump sizing, that's not always the case either. We have, so you say you're designing the pumping system for a residential building or commercial building to maintain water pressure throughout the system, or a city municipal water supply where you want to maintain 50 pounds per square inch to individual households. So then you have to deal with the flow rates and the pressure. And so your P1 and your P2, your P1 might be the pressure in the beginning of your system, and P2 might be the pressure at all the endpoints of your pump array system or your piping system for the municipal water supply, and that one needs to maintain 50 pounds per square inch. So, but for our particular purpose, we're going to say that we're pumping from one reservoir to a large tank that's also open to the free surface, so our pressure is going to be 0 on both ends. And then because both of these are large reservoirs, we can assume that the velocities in those two are 0. And if you're doing a municipal water supply, you can often do the same thing, because you'll be going from a large reservoir to a bunch of individual little points that will be taking flow out at a much lower rate. And so really what's going to be driving it is the 50 pounds per square inch that you need to maintain. So we can get rid of those. We need to keep Z1 and Z2. We need to keep head losses. And in this case, we have no turbine. But again, as I mentioned before, turbine sizing is very similar. It's just instead of adding energy into the system, you'll be extracting energy out. And it really comes down to looking at some of the manufacturer's details in your requirements and finding something that works right for you. Okay, so what we can do now is simplify this and rearrange. And so what we get is, in this case, you get H sub P is equal to Z2 minus Z1 plus H sub L. Okay, and we can rearrange this a little bit and make something a little bit more convenient for us to look at, and that's H sub P is equal to delta Z, which is just the change in height, so that's the difference between 1 and 2, Z2 minus Z1, plus, And I'm going to rearrange this and add some things in there. And so we're going to have is alpha plus FL over DH plus K sub L times V squared over 2G. Okay, so what I've done here is assumed for this general purpose that our V1 and V2 are not negligible, and so we keep alpha. FL over DH is our typical head loss times problem, and then KL is dealing with the fittings. So what I did was I just pulled V squared over 2G out, and for our particular case, where the V's are 0, this alpha goes out, so that would be 0. And so we end up with H sub P is equal to delta Z plus, what's it, really H sub L, but it's going to be F L over DH plus K sub L, V squared over 2G. Okay, and so this is the requirement for the pump, that we need to have that much pressure head in order to get the water from one place to another. The next consideration is the flow rate. So if we think about it, when we're doing design, we often want to have a particular flow rate. And what you see here in this equation is that H sub P is a function of the velocity, which by definition makes it a function of the flow rate, Q, because V is equal to Q over A, right? And so the pressure you need for the pressure head that you need, or the pump head that you need for a particular system, is going to depend on your flow rate design constraints. And so what happens is you get something that looks like this, where the pump head required is a function of the velocity or the flow rate. And I drew this out here. It looks something like this, where your initial point at 0 velocity here is going to simply be your delta Z, right? If you don't want any flow, the pump, you need to have enough head to overcome that elevation change, that potential energy change. Then anything above that's going to be head losses, and so you have this curve that looks like this. And so if you have a design here, a flow rate here, then you're going to come up here, and this is going to be your head loss. Okay, and so you need to know something about the flow rate. Okay, so you can take that to the next step, and as I mentioned earlier, what we do is pumps have a curve called a pump performance curve, and they're provided by the manufacturers of the pumps, and they look something like this. This is for a particular manufacturer, but and in several models of their pumps, and some of them at low speed and high speed, where the pump provides a certain amount of total head that is dependent on the flow rate, because the pump's partitioning the amount of head it can really generate. So for example, this particular pump here can provide almost 80 feet ahead at no flow rate, but as you increase the flow rate, then the power is going, instead of into the potential energy here, it's now being divvied up between the kinetic energy and the potential energy. And so as you increase the flow rate, more kinetic energy, there's less potential energy available. So that's basically what's happening with pump sizing. And so what you want to do then is you look at a curve that looks something like this, where this is the pump performance curve in the dashed line, like this. So that looks just like the curves we had before, where the shutoff head, or if you have a head greater than this, you're not going to get any flow rate. So there's the shutoff head. And then you have your performance curve here, and the operating point of the pump is going to end up being where those two intersect. Okay, so if you have a particular system and you put a pump in there, it's going to operate where those lines intersect. But you really don't want to just arbitrarily choose a pump and have that and hope that that intersects. What you want to do is have a design flow rate, and then pick a pump that gives you an intersection with the pump performance curve at that point. Okay, there's one more step to this that needs to be considered, and that's shown here in this last figure. Is there's also an efficiency curve. So pumps often have an optimal efficiency, where the efficiency curve is this curve here, where there's a point here with the highest efficiency. And the efficiency is defined, so eta, the efficiency, is equal to the work rate of the pump divided by the work rate of the shaft of the pump. So that's equal to m dot g h sub p divided by w dot shaft. W dot shaft will be often reported by the pump. So you might have a 3 kilowatt pump or a 5 kilowatt pump or a 1 horsepower pump or a 5 horsepower pump. That's W dot of the shaft. And then your W dot of the pump is going to be your HP, which is dependent on the flow rate, times m dot g, which is also, the m dot's going to be dependent on the flow rate. So you have a situation where you have the work rate of the pump is dependent on that flow rate. Okay, so if you had a pump curve, and these are also published, the figure I showed before didn't show this, but if you have a pump performance curve, is often published with the efficiency curve. In fact, they'll be on the same plot like I show here, where they actually show the amount of power that the pump's putting in, the efficiency, and that head pump performance curve or head discharge curve. And so what you would want to do is, if you were here and you said, okay, if I'm looking at my head requirement curve and my operating point is going to be, say, here, then what you're going to do is when you go to the pump performance curve, you're not just going to pick a pump that fits, say, here. You're going to pick one whose head discharge curve intersects your head requirement curve near the point of highest efficiency. Makes sense, right? So you're going to maximize the efficiency of a particular pump, and that's really how pumping design works.